Hey guys, so this video is going to be a quick video on the physics of free fall. So when an object is in free fall, we're going to assume that the only force acting on the object is the force of gravity. So for this class, for almost all the problems, unless I tell you otherwise, we're going to assume that there is no air resistance acting on the object. And so really there's only one force we have to worry about, and there's only one acceleration we have to worry about. So, as we said in class, forces cause acceleration, and we'll look at this a lot more in the next chapter. But gravity will cause a constant acceleration downward. So keep in mind when we're looking at situations involving free fall or when we're solving problems in free fall, that the acceleration is going to be pointing down, which is important when we get to our coordinate system. So at sea level on Earth, which is where we're going to solve most of our problems, we're going to assume that most of our locations are close to the sea level of Earth. This acceleration due to gravity has a magnitude of 9.81 meters per second squared, and we're going to give this a variable, and we're going to call this little g. Okay, and that's to contrast that with big G, which we'll see later on in the course. Okay, so one of the things about the problems involving free fall is you won't be given this explicitly. It's kind of assumed knowledge. You're gonna just have to realize that that's the acceleration. It's not gonna be given to you in the problem, so keep that in mind. Now, because the acceleration due to gravity is constant, we can use the kinematic equations that we just learned for accelerate motion in order to solve problems. Our acceleration is not changing. And as we discussed, any situation where we have a constant acceleration, we can use the kinematic equations to analyze its motion. Now, an important thing with free fall, which seems counterintuitive, is that the mass of the object does not matter. So when you look at the kinematic equations, there's no mass in those equations. And when we look at the motion of free fall, the mass of the object isn't going to matter. And again, we don't usually see that, because of air resistance that's all around us. But again, in this idealized situation, we are going to assume there is no air resistance, and therefore the mass of the object is going to essentially cancel out. You can understand it as the force of gravity is greater on heavy objects, but heavy objects have more inertia, and so it's harder to accelerate them. So the greater force gets kind of offset by the fact it requires more force to cause the same acceleration. So let's look at a problem involving a bowling ball. Okay, kind of a straightforward, good start or free fall problem. So a bowling ball is thrown up in the air at a speed of 5 meters per second, and we're going to ask what height will the bowling ball achieve. Okay, so as we always want to do, we want to start with our diagram, and so we're going to have a little bowling ball, and we're going to throw it up at 5 meters per second, and that's going to be my initial velocity. I'm going to say my initial velocity is 5 meters per second, and I'm also going to make up my positive direction, so setting my coordinate system. So this is going to go up to a certain height, okay, and I'm going to call this height delta x, and that's going to be my unknown for this problem. How high will this go? How high above the release point will this go? Now, as I said, what's not shown in the problem, but which is important, is the acceleration due to gravity. It's not mentioned, but I realize that this acceleration due to gravity is going to be acting downwards, and because it's acting downwards and my coordinate system is positive, this acceleration due to gravity is going to have a negative 9.81 meter per second squared value. Okay, so that's what I know. And then there's one other thing that I know, which is not in the problem, but you have to get it from thinking about the physics of the situation, or at least what's going to be going on. Like, what would you observe going on? So that is, when I throw this ball up in the air at 5 meters per second, it's going to go up, 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 up. And when it gets to this maximum height right here, it's going to stop momentarily, okay? Which means that my final velocity is going to be 0 meters per second, just for a bit. As I said, gravity keeps on acting on this. It's going to keep on accelerating. That velocity is going to change, and eventually it's going to have a downward velocity, and we know that. But at that instant in time, when it's at the top, its instantaneous velocity is going to be 0 meters per second, and that's going to be valuable for us to know. Okay, so when I think about my knowns, my unknowns, to kind of get them all here, what do I know? I know that my acceleration, which I'm going to call little g, is going to be negative 9.81 meters per second squared. I know that my initial velocity is going to be a positive 5 meters per second squared. I know that my final velocity is going to be 0 meters per second squared. And the unknown that I have in this problem is this distance, delta x. Okay, and that's what I need to solve for. Okay, so when I think about the concepts involved with this problem, okay, so we want to think of the concepts. When I look at this problem or problems like it, the first thing that I think of are two things. I say, oh, this is first of all a free fall problem. Okay, so only gravity is going to be acting on this, so it's going to be a free fall problem. The other thing we're going to think about as far as concepts go is that this is going to have constant acceleration. Therefore, I use 3 dots for therefore I can use kinematic equations. Okay, so this is the free fall problem, and I can use kinematic equations. So those are the concepts. And now I'm going to think about what equations I can use to solve for this problem. Okay, so what equation or equations am I going to use? And so I look at my knowns, I'm going to look at my unknowns. And the possibilities here, and I don't expect you guys to write out all your kinematic equations, but the possibilities, if you look at the kinematic equation, we have Vf squared is equal to V naught squared plus 2a delta x. Or I could say that delta x is equal to V naught times time plus 1/2 at squared. Or I could say that the final velocity is going to be equal to my initial velocity plus the acceleration times time. Now notice that since I don't have time, okay, time is not given to me in this problem, I'm not going to use this and I'm not going to use this. I can't. Unless I find a way to use time, I can't use those. So I'm going to use this equation right here. I know my final velocity, I know my initial velocity, I know my acceleration, and it has what I want to solve for. So that's perfect. Okay, so now I'm going to start solving. Okay, this is going to be my solution. I'm going to start solving for this. So what I'm going to do is I'm going to take this top equation here, I'm going to rearrange it to solve for delta x. So I'm going to do a little bit of algebra, and I'm going to get delta x is equal to Vf squared minus V naught squared divided by 2a. Again, if you need to write out the steps or you get lost in the steps, feel free to ask, but prove it to yourself. That's going to be the equation. And I want you guys to solve these equations in terms of variables whenever possible, because it really will make your life easier. And there's a lot of problems in the AP Physics 1 exam itself that ask you to just do this, just derive the equation in terms of variables. So I want you guys to get in the habit of doing that. So now I have this equation. I'm going to plug in my numbers, and so this will be 0 meters per second squared for my Vf minus quantity 5 meters per second squared. And I have to square that, don't forget to do that. To square the whole thing, times 2 times negative 9.81 meters per second squared. And I do all that, and I solve, and I'm going to get to the limit of sig figs 1.3 meters. Okay, so this is going to be my delta x. This is my height that the bowling ball is going to go, and that seems pretty reasonable. It's a little over 3 feet, so I didn't throw it up that fast. It was only 5 meters per second. I know it's tempting to think, well, the bowling ball's got a lot of mass to it. So, but again, mass doesn't matter for this. But the initial speed wasn't that great, so it's going up, but it's not going up too much. And so the check, this mental check I want you guys to do works out too. All right, so that's how we do a free fall problem. And in class, we'll look kind of the more conceptual stuff, like how distance changes with time and free fall and so on and so forth. But yeah, I hope this sample problem kind of gave you some guidance on how to solve these problems. Again, the big points are that the acceleration is going to be constant. It's going to be pointing downwards. Unless told otherwise, you can assume it's going to be 9.81 meters per second squared. and when the object is at the top of its path, when you throw it straight up, it's going to have a 0 velocity, and that's something that's not always going to be given to you. So I hope this helped, and if you guys have any questions, please ask me in class.